Okay, the example is, let's say 10x mod 5, 10x congruent 5 mod 15. So here, what is the GCD? GCD of 10 and 15, as we know, it's 5, which divides 5. So we are in case 2.2. And what was the recipe in case 2.2? Well, we have to write, if the GCD is D and B is a multiple of D, we have to write all these three numbers, which in our case are 10 and 15 and 5, as a multiple of 5 first. So 10 is 5 times 2, 15 is 5 times 3, and 5 is 5 times 1. So that means we want 5 times 2 to be congruent with 5 times 1 mod 5 times 3. And we saw that justified above, that we are allowed to cancel 5 and divide all these numbers by 5. Because if you look at the recipe in case 2.2, we said that AX congruent B mod M has the same solutions as A prime X congruent B prime mod M prime. And what are A prime, B prime, N prime here? These are the numbers where the original numbers, these are the numbers obtained by dividing the original numbers by D, the GCD. So if I divide A by GCD, I get A prime, M by GCD, I get M prime, and B by GCD, I get B prime. So we justify that these two congruences have the same solutions. So that means we can divide everything by 5, and then we get 2x congruent 1 mod 3. So we are left, we have reduced our problem to 2x congruent 1 mod 3. And now, as we expect, we have reduced the problem to a problem from case 1, where GCD of A and M is 1. So now GCD of 2 and 3 is 1. So that means I have to multiply. Do you remember the algorithm in case 1? We have to multiply both sides by inverse of 2 mod 3, namely, what is it, inverse of 2 mod 3? Of course, we have an algorithm to find the inverse, but because in the case that the numbers are small, you can just find the inverse by inspection. Just check one by one. 2 times which number is 1 mod 3? Well, 2 itself. Because 2 times 2 is 4, which is 1 mod 3. So if I multiply everything by 2, I get 2 times x. Mod is congruent 1 mod 3, and 2 times 2 is 1. So that means x congruent 1 mod 3. So the solutions, the set of all solutions is any number of the form 1 plus 3k, where k comes from z, right? So x congruent 1 mod 3 means x is of the form 1 plus 3k. All right. Now the next subsection basically is a Chinese remainder theorem. Chinese remainder theorem. So the goal here is to solve a system of congruences of the form let's say X congruent A1 mod M1, X congruent A2 mod M2, all the way to X congruent AK mod MK, where M1 to MK are pairwise relatively prime. Okay, so in elementary school and middle school, first you learned how to solve one equation. Let's say 2x equals 5, for example. You learned how to solve it. But after that, you learned how to solve a system of equations. Let's say, for example, two equations with two unknowns. For example, x plus y equals 1 and 2x plus 5y equals 6, for example. So you learn system of equation means solving two or more equations simultaneously. In other words, finding, for example, x and y values that satisfy both equations. If you have two equations, finding x and y values that satisfy both equations at the same time. So here also we learned how to solve one congruence. But what about if you have few congruences of this form? Let's say x congruent A1 mod M1 all the way to x congruent AK mod MK. Can we find the value of x or find all values of x that satisfy all the congruences at the same time? So we are looking to find the x values that x mod M1 is A1. At the same time, the same x value mod M2 is A2, and so on. Okay. So for example, let's say if you want to solve, for example, x congruent 1 mod 3, and let's say x congruent 3 mod 7. A solution for this system, let's say one, or a solution for this system is x equals 10. I'll tell you how to solve the system systematically, but just to start, just to get an idea, let's say if you have a system of two congruences, x congruent 1 mod 3 and x congruent 3 mod 7. So in other words, if you're looking for a number that when you divide it by 3, you get the remainder of 1, and when you divide it by 7, you get the remainder of 3. But by inspection, we can see that x equals 10 is one of those numbers. Why? Because 10, when you divide it by 3, you get remainder of 1. When you divide it by 7, you get remainder of 3. So 10 is one solution here, because it satisfies both congruences at the same time. But of course, we could ask, are there any other solutions other than 10? Or can we find all the solutions? And also, how about if the numbers were big, or the number of congruences were more than 2? And in that case, it would be hard to guess by inspection. Is there any way to solve this system, systematically? Or finding an algorithm to solve this system? So the answer for this question is given by a theorem called Chinese remainder theorem. It's called Chinese remainder theorem because it's a heritage of basically a Chinese work that the way that they solved this type of problem or similar problems. So that's why this is called Chinese remainder theorem. So theorem Chinese remainder theorem. So let M1 to MK be relatively pairwise, relatively prime numbers. Then the system. The system that I just described above, X congruent A1 mod M1 all the way to X congruent AK mod MK, has a solution. Moreover, so that's a good news. It has a solution. Moreover, the solution is unique mod M defined as M1 times M2 times MK. Okay, so once you find one solution, then that means you have found all the solutions, because the solution is unique mod M. M is M1 to MK, right? So if you want one solution, that means if you need other solutions, every other solution is original solution plus a multiple of M, right? When we say a solution is unique mod M, means any other solution is same as original solution, but plus maybe possibly a multiple of M. So for example, before proving this theorem in example above, by inspection, we found that X equals 10 is a solution for X congruent 1 mod 3, X congruent 3 mod 7. So what does this mean? So any solution is of the form X equals 10 plus MK, right? Because the solution, since the solution is unique mod M, which is M1 times M2 in this case. M1 times M2 is 21 in this case. M1 is 3, M2 is 7, so M1, M2 is 21. So that means the set of all solutions is ten plus 21K, where K it comes from Z. So 10 is one of them. If you need the next solution, is going to be 10 plus 21, which is 31. We can check that 31 is 1 mod 1 and 31 is 3 mod 7, and so on. So the next solution will be 10 plus 2 times 21, 3 times 10 plus 3 times 21, and so on. Okay. Now, let's see how we can prove this theorem. Proof of theorem. The proof is important because not only proves the theorem, it also provides an algorithm how to find a solution for this system. Okay, now I'm going to set a number defined as capital, let's say ML. So set capital ML as this number M, which if you remember was the product of all MIs over ML. It's going to be M1 times M2 to MK over ML. And this is same as the product of all MIs except ML itself. So M1 times ml minus 1 times ml plus 1 all the way to mk. So this is the number, this number here, I'm going to call it capital ML. Now the important feature of this number capital ML is that it's relatively prime with small ml. Now GCD of capital ML and ML equals 1. Why? Because if not, if GCD of capital ML and ML equals, let's say, some D, which is bigger than 1, then what can I say? Then I can say that some, let's say, prime number P divides ML and P divides ML for some prime number P. If GCD is bigger than 1, then some prime number P will divide both number capital ML and small ml. And I want to reach a contradiction because I want to show that GCD is 1. So if it's not 1, then at least some prime number, well, at least one prime number divides both of them. So what does that mean? So that means P divides, what was capital ML? Capital ML was M1, M2, ML minus 1, ML plus 1 to MK, and P divides ML. Now this one implies that P divides MJ for some J by property P divides AB implies P divides A or P divides B. If you remember last time, I think towards the end of the lecture, we showed that if a prime number divides product of two numbers, then it divides one of them. Now, similarly, this can be generalized as if a prime number divides product of few numbers, then it's at least it divides at least one of them. So P divides M1 to ML minus 1, ML plus 1 to MK, product of these numbers. So divides at least one of them, which means P divides MJ for some J not equal to L. So now P divides MJ with J not equal to L, and P divides ML, right? The other assumption here, P, or the other result here, P divides ML. So these two together means that GCD of MJ and ML must be bigger than 1. If MJ and ML have a common divisor P, which is already bigger than 1, P is a prime number, then of course the greatest common divisor between MJ and ML is still bigger than 1. And this is contradiction with MJ and ML being relatively prime. Right? Remember, the assumption of Chinese remainder theorem is that you have some numbers M1 to MK, which are pairwise relatively prime, which means any two of them that you consider are relatively prime, meaning that their GCD must be 1. Okay, what have we shown so far? So we showed a GCD of capital M L and ML equals 1. Equals 1 for every L between 1 to K. Now, if GCD of two numbers is 1, then what equation can I say that, or what congruence can I say that it will have a solution? Thus, capital ML times X congruent 1 mod ML will have a solution. Case 1 above. Remember, we talked about the solution of congruence. When do we say that a congruence has a solution AX equals B mod M? If GCD of A and M is 1. Right now, my A is capital ML, my M is ML. And GCD of these two numbers is 1, so AX equals B will have a solution. So MLX congruent 1 mod ML will have a solution. So call the solution XL. Or let me say, and write it this way. Let XL be a solution for this congruence. So I can say capital ML times XL congruent 1 mod ML. Okay. So lastly, set X equals A1 M1 X1 plus all the way to AK MK XK. Remember, what is my goal? My goal is to find the solution X for this system. But there you are. I'm claiming that the solution X that we are looking for is exactly this X that is defined here. So claim is X as defined above is a solution for our system, which was X congruent A1 mod M1 all the way to X congruent AK mod MK. Now to verify the claim, how much is X mod A1? How much is X mod M1? So X mod M1, we want to know what's the answer. What is X? X is A1 M1 X1 plus A2 M2 X2 all the way to AK MK XK. Now, what is M2, capital M2? Remember how we define capital ML? Capital ML we define it as product of all MIs except small mi itself. So capital M2 will be the product of all MIs except small m2, which means it's going to be M1 times M3, right? Let me write down what M2 is. M2 is M1 times M3 all the way to MK, which is a multiple of M1. And if a number, because it's M1 times something, right? And if a number is a multiple of M1, then that means mod M1, that number is 0, right? So from the beginning of today lecture, we repeatedly use this fact that if a number is a multiple of M, then mod M, that number is 0. So that means A2, M2, X2 is 0 mod M1. Similar reasoning for this, MK is M1, M2, MK minus 1. Again, I can say it's a multiple of M1. And therefore, again, this number is 0 mod M1. Thus, so see, X is A1 M1 X1, A1 M1 X1 plus bunch of terms which are all 0 mod M1. So what can I say about X? So X is A1 M1 X1 mod M1. But how much was M1 X1 mod M1? So let me call this congruence star. MLXL mod ML is 1. So M1 X1 mod M1 is 1. So this is A1 times 1 by star above mod M1. That means X is A1 mod M1. So I showed that X is A1 mod M1. Similarly, we can show that X is A2 mod M2 all the way to X is AK mod MK. So the type of reasoning that I said for M1, very similar reasoning you can say for M2, but for M2, of course, this term will survive, and first term, third term, fourth term, all the way to K term, they will be all 0 because these are multiples of M2. But second term will survive, and M2 X2 again is 1 mod M2. Therefore, second term will be A2 times 1, which is A2, and so on. Okay. Now let's look at an example. Okay, by the way, for uniqueness, so proof of uniqueness. Exercise. So it will be in the next homework, which I will upload by the weekend. Yeah, in the homework, in the book exercises, one of the book exercises, it asks you to prove the uniqueness. But remember, uniqueness, of course, is mod M, not, let me emphasize here, mod M. So the solution is not unique. You can have more than one solution, but any two solutions that you consider, they are equal mod M. So they may not be equal, but they're equal mod M, meaning that they're congruent to each other, mod M. Okay, so now let's look at an example. Find a solution. Let's say find all solutions for the following system. Now the system is X mod X is 2 mod 3, X is 3 mod 5, X is 2 mod 7. So we are looking for all numbers X that when you divide it by 3, we get remainder of 2. When you divide by 5, you get remainder of 3, and you divide by 7, you get remainder of 2. So any number X that you introduce must have all these 3 properties at the same time. So that makes the question a little bit difficult, because of course, if you want to solve this separately, it's very easy to find the value of X that is that has remainder 2 when you divide by 3, for example, 5 itself. But for example, 5, when you divide it by 5, you don't get remainder of 3. 5 divided by 5 get remainder of 0, right? So solving each of these 3 congruences is very easy, but we are looking to find the values of x that satisfy all 3 of them at the same time, not separate. Okay, so first, the solution. First, so if you want to use the recipe provided by Chinese remainder theorem, remember, whenever you want to apply a theorem, first you need to check the conditions of the theorem. Do the conditions hold here? If the conditions hold, then you can apply the theorem. The condition of Chinese remainder theorem is that you have a few numbers m1 to mk, the modules, but those numbers must be relatively pairwise, relatively prime. So here, m1 equals 3, m2 equals 5, m3 equals 7, and these numbers are relatively prime because GCD of 3 and 5 is same as GCD of 3 and 7, and this is same as GCD of 5 and 7, and this is same as 1. So these are pairwise. M1, M2, M3 are pairwise, relatively prime. So that means we can apply Chinese remainder theorem and use, let's say, equation 2 star to find the solutions. Let me call this equation 2 star. So Chinese remainder theorem, or maybe this one was appeared first above this. So let me call that equation the first time it appears and call it 2 star. The Chinese remainder theorem tells us that if you want to solve the system, the solution x can be given by this equation, a1 times m1 x1 plus a2 m2 x2 a3 m3 x3 and so on. So right now I have only 3 of them. So x is a1 m1 x1 plus a2 m2 x2 plus a3 m3 x3. So let's see what these numbers are in our case. A1, A2, A3 are the ones given in the question, which are 2, 3, 2 here. So A1 is 2, A3, A2 is 3, A3 is 2. So this one is very easy to find A1, A2, A3. What about M1, M2, M3? That's also easy to find. M1. So let's look at how we define capital ML. In the beginning of the proof, I told you that capital ML is M, small m, and a small m means product of M1 to MK divided by ML. So capital M1 is M1, M2, M3 divided by M1, and so on. Capital M1 is M1, M2, M3 divided by M1, which is of course same as M2, M3. So capital M1 is the product of all MIs except M1, small m1, which means M2 times M3. And how much is that? M2 and M3 were 5 and 7, so that's 35. Similarly, capital M2 is M1, M3, product of all MIs except M2. So that's M1 times M3 is 21. And capital M3 is M1, M2. Product of M1 and M2 is 50. And then I need also X1, X2, X3. X1, what was XL? XL, again, if you go back to the proof, XL was the solution for MLXL equals 1 mod ML. Next, find X1, X2, X3 using, again, star above. So I want M1 X1 to be equal 1 mod M1. So that means M1 was how much? 35. 35 X1 equals 1 mod M1. M1 was 3. So how much will this X1 be? X1, you can check that it's 2. Yeah, X1 will be 2. Check by inspection or using algorithm we derived to solve AX equals B mod M. So you already know how to solve AX equals B mod M as long as A and M have GCD 1. Well, here GCD of 3 and 35 is 1, so we can solve it using the algorithm. Or as I said, in the case that the numbers are small or it's easy to guess, you can first try to guess. So GCD of 35. I mean, of course, if the question says use the algorithm, then you have to use the algorithm. But otherwise, we can just try to guess, especially if the numbers are small. Now GCD of 3 and sorry. So if you want to guess, so 35 times 2 is 70, and 70 is 1 mod 3. Why? Because 3 divides the difference between 70 and 1, which is 69. So X1, the solution for this is 2. Now M2 X2 equals 1 mod M2. So this means how much was M2? M2 was 2. And no, say 21. 21 X2 was 1 mod small M2. Small M2 is 5. Now how much is this number? Again, by inspection, we can guess. We can use X2 equals 1. Right? 21 times 1 is 21 itself, which is 1 mod 5, because 25 divides the difference between 21 and 1, of course. So this one, as I said, if it's easy to guess and the question is not asking you that, to use an algorithm. So it's not asking you to use the algorithm to solve the congruence, then you can guess. 21 times 1 is 1, which is 21 times 1 is 21, which is 1 mod 5. So this one was very easy to guess. So you can say by guess or by inspection. Now M3 X3 equals 1 mod M3. So that means M3 was how much? M3 was 15. 15 X3 1 mod M3. M3 was 7. So 15, again, see, X3 equals 1, again, is a solution. Why? Because 15 times 1 is 15, and 15 is 1 mod 7, right? Because 15 minus 1 is 14, which is divisible by 7. So there you are, we found X3, X2, X1. We also found M1, M2, M3, and we also found A1, A2, A3. And these are all the numbers that we need to find X. Thus, X is equal to A1, M1, X1. So going to be 2 times 35 times 2 plus 3 times 21 times 1 plus 2 times 15 times 1. And the answer is 233. 233. So we can also verify. So please verify your answer by checking that 233 is 2 mod 3, and 233 is 3 mod 5, and 233 is 2 mod 7. See, we were looking for a number X that is 2 mod 3 and 3 mod 5 and 2 mod 7 at the same time. And 233 is the number that we were looking for. It satisfies all the 3 congruences at the same time. So this is one solution. And then if we need all the solutions, what should we do? The set of all solutions is going to be this, the first solution plus mk, where k is an integer. Remember, the solution is unique mod m. Means what? Means any two solutions are congruent mod m. In other words, every solution can be written as one of the solutions. In this case, 233 is this one of the solutions that we found, plus mk. And what was m? M was the product of m1, m2, m3. That's going to be, how much was it? M1, M2, M3. 3 times 5 is 15 times 7, 105. So this is 233 plus 105 times k, and k comes from the set of integers. So the meaning of the solution being unique mod m means that any other solution can be written as the first solution plus a multiple of m. So one solution is 233. So any other solution can be written as 233 plus a multiple of m, and m in this case is 105. Okay, so we found solution to be 233. We verified that it satisfies all the three congruences at the same time. And then the set of all solutions is one solution plus an arbitrary multiple of m. Okay, guys, so this is about Chinese remainder theorem.